So we've talked about Bohr model, and then we talked about quantum mechanics. And in quantum mechanics, there was quantum numbers that told us where the electrons exist, but they're in these orbitals. So they're in these like three-dimensional shapes. And the numbers that represent them were the shell, which told you about how far it was from the nucleus, L, which gave you the three-dimensional shape. M sub L, which you'll see down here, is going to be the number of orbitals that the electrons can be in. And remember, 2 electrons can go in each orbital. So these 3 quantum numbers are describing the most probable location of these electrons. So we're going to use those 3 in these notations that we have to write out electron configurations. So those electron configurations are given the locations with these numbers of each electron in an atom. So we don't just want to know electron configurations, because for any element you can have multiple excited states. So we want to know when it's in its ground state. So for however many electrons it has, there's a certain electron configuration when it's in its lowest possible energy configuration. So it's like electron configuration, but we call it the ground state electron configuration. So how do we show this? We're going to do a lot of examples, but this is a good start. There's 3 different ways that we can represent this. So let's start off doing kind of a simpler one. I don't want to do something so simple as hydrogen because you're not going to see the pattern as much. So let's start with lithium. So still a low number, but we'll start with this. So if you look at your periodic table, so if you want to, you can pause right now and go find the periodic table we've been using in class, because then you can notate it. Even if you have a printer and you print out a black and white version, we're going to start filling this in with the videos. So lithium, let's just look right now at lithium. So lithium has a 3, if you can see on your periodic table, the little number 3, which is the atomic number, which is the number of protons, but that is also the number of electrons for a neutral atom. So for lithium, we got to figure out, with the ground state electron configuration, where those electrons have a high probability of being. So we have our N, our L, and then this is going to represent the M sub L. So the N starts with 1, could go 2, 3, 4. So this is the lowest, N equals 1. For N equals 1, you can have an L shape of S. So for that L shape of S, you can have 1 orbital. And in that 1 orbital, you can put 2 electrons, because you can put 2 electrons in each orbital. And I'll keep saying this over and over again when we do more examples. This one, that's still the N. So N equals 2 for that one. L is still an S shape. And then I'm only putting 1 in here, even though it could hold 2, but I only need to put 1 because I'm just trying to find the lowest energy level for the 3 electrons that are in this lithium atom. So 1, 2, 3, and based on the rules that we had for our quantum numbers. And there's a good chart for those in the book, for the orders of them. This is a different way to show it. So each one of these purple boxes, it's all lithium, but it's different ways that we show it for different reasons. So this one, notice it still has the 1s and the 2s. So those electrons are still in the same energy levels or orbitals. Here, those 2 electrons are represented by arrows, and we'll talk about why one's up and why one's down, but they fill in this way, 1 up, 1 down. This, just like there was 1 electron over here, there's 1 electron here in the 2s. We show the arrows up and down, and again, we'll talk about that in a second. The last is what's called the noble gas electron configuration. And we'll do more examples, but really quick, for lithium, you would go backwards to the noble gas. Remember, that's this last column. The noble gas before it, which is helium, and then put how many electrons would appear after that noble gas. And we'll go into more detail when we do those, but this is a a good starting point for explaining how we're going to show these ground state electron configurations. So we're going to do some more examples like we did of lithium, but we're going to do some higher numbers, and I tried to get high enough that you'd see the good variety of how we're going to do this. What you need to get before we start, because I have such a little whiteboard, is I want you to get this, print out this, or just have the slide available. So that's chapter 5, slide 26. And then, like I said last time, have your periodic table out so you're ready to look at that and write on it. And then I want you to have slide 36 and 37 available, because instead of writing out all of these definitions, I'm just going to kind of point them out on this slide so you can go back later and look at the definitions as you watch the video again, and you kind of pause and remember those definitions. It's not necessarily remembering the definitions, it's remembering how to apply them over here. That's going to be important for the quiz. So let's go through and look at the different designations that we had before, which was writing out the electron configuration, the orbital filling diagram, and the noble gas electron configuration. So we'll start with carbon. We have to figure out the number of electrons, and like last time with lithium, we went up to the periodic table, we saw what the atomic number was, and that tells us the number of electrons if it's a neutral atom. These all are. So we're going to fill up our orbitals from the lowest energy up. Filling up from the lowest energy up is part of the off-ball principle. So the off-ball principle is called building up, because you're filling up the lower energy orbitals first, putting 2 of them, 2 electrons in each one of these orbitals like we did for the lithium. And then we'll talk about what degenerate orbitals are when we get to that point. So this is where I want you to come over to this table. So this is how I was writing the 1s, 2s, how I need to write them in that order. So remember, the 1 is the N. The L0 is the one, if you go back, the one, or L equals 0 is the S. And then if there's one value here for M sub L, it means there's only one orbital available. So that's telling you that this is the lowest energy level is a 1s. And over here it says 1s. And then number of orbitals in the subshell is how many M sub L. So this all goes together. So kind of have that so you can look at it when we're going through. So it's, you get 1s. And then 2s, because L equals 0. Maybe we'll write that on this one. And then 2, L equals 1 is a P. So that's what we have over here, but that's what these designations are telling you. As you go down, you're increasing in energy, and the off-ball principle is telling you that you're filling the lowest energy ones first. So we have to go down through that list. So we have 1s, and then 2s, and then 2p. So 1s, 2s, 2p, we could put 2 in the s. So you could have 1 orbital in the subshell. We can put 2 electrons in an orbital. So 1s, 2s, 2p. 2p can go up to 6. We'll talk about that, but it only has 2 in currently. So we put our 2 in our 1s orbital, and remember these are representing the electrons. So it's 1s, 2s, still just 2, because that's the most that we can put on a line, because the line represents an orbital. When we get up to 2p, if you look back up here, so it's 2p, See how there's 3 of those M sub L values? That's telling you that those are the number of orbitals in the subshell. Those lines represent the orbitals. So of those 3 orbitals though, we're only going to put in 2 of them. So these 2 electrons go in different orbitals. That is Hund's rule. So the fact that I put one of these in each one of these orbitals is based on the fact that it's lower energy to fill these orbitals singly, so 1 electron in each, before you start pairing them up. Think about the fact that electrons don't want to be next to each other, so to have them in the same orbital would be higher energy than having them separate. So a bunch of these definitions go along with this. So the 2p has these 3 orbitals. We have to fill them based on the lowest energy level. If they are degenerate, they are all the same energy level, which is the definition for degenerate. Hund's rule tells us that we have to fill them up singly first before we pair them up. So as we go through here, we only have to put 2 in because we only had 6 electrons in the carbon, and we filled them up until we got the P, but at that point we only needed to put in 2 more to get to 6. Noble gas electron configuration, and you'll see the pattern as we go down, is you look at carbon, you go backwards to the last noble gas before it. You have to put that in little brackets, and then you add on the electrons after that noble gas. So after that noble gas, we've already put those 2 electrons in. Those 2 electrons were in this 1s2 orbital. So it's like helium is this, and then we're adding on that part. It doesn't seem to like really help yet, but when we get further down, it really shortens the notation and only shows the most valuable electrons for reactivity. Let's do the next one. So sulfur, if you look at sulfur, so sulfur's down here, atomic number 16. So neutral sulfur will have 16 electrons. We start filling these up, so I'm not going to go through sending each one of them, but if you look up here, you can see the orbital notation and how we're filling them up based on their energy levels. I'm going to have us do together the orbital filling diagram that we have here. So I would pause the video if you want to try to do it yourself, and then we'll do it together and talk about the definitions. Okay, so we know the 1s is full, the 2s is full, the 2p is full. I'm gonna show myself filling them based on Hund's rule, but they're all just gonna fill up anyway. The 3s is full, as it's 2. 3p, we're only putting the 4 in there that are necessary for sulfur. When we fill based on Hund's rule, we are supposed to put 1 in each one. So 1, 2, 3. Once you've put 1 in each one, each orbital, you go back and then you start pairing them up. So it had to be paired up because we had already filled up the other orbitals. And then the noble gas electron configuration, we'll see how that's shortened, because the noble gas before sulfur is neon. So if you go back, the noble gas before sulfur, it's neon. So if I put neon in brackets, I just have to add on whatever the electrons are in after that. So neon is all of those electrons. So if you look, Neon has the atomic number of 10, so 10 of these are the same thing as red and neon. So it's just a way of showing what the outer electrons are. So the ones on the very outside are the ones that come after that noble gas. Next one down. Okay, so we did Hund's rule on that one. We're filling based on the off-ball principle, which is the lowest energy up. These are all the ground state configurations. Degenerate orbitals was orbitals that had the same energy. So these are degenerate with each other. But this one's not relative to these because they're not the same energy level. So summary again of our definitions. Last one, vanadium. So vanadium, look at your periodic table. It's atomic number 23. So 23 electrons for neutral vanadium. And then we just start filling them up. So we got the 1s, 2s, 2p, 3s, 3p. When you get to this section, it's a little strange, and you just kind of have to believe me until I show you something else. But instead of 3s, 3p, and then 3d, the 4s actually comes before the 3d. Based on the off-ball principle, if we are writing it this way, that is because those electrons in the 4s orbital are actually lower energy than the ones in the 3d. And it has to do with the shapes of these, but we'll do a summary of that when we get to talking about atomic radii. So I want you to try to fill in. So pause the video and try to fill in this orbital filling diagram, which I kind of had to shove over here. So fill that in and then we'll talk about it. So all of these are filled up until we get to the 3D. So all of them have their maximum number of electrons. And again, this is full, but I'm going to show based on Hund's rule. When we get to 3D, it's not full. And 3D only has 3. There are 5 orbitals in a D. So if you look back up here, when you have a D, there are 5 orbitals in the D subshell. So you have to put 5 lines because that's showing the 5 orbitals, but we're only putting in 3 of them. So think about whose rule is telling me to put 1 in each. So that's Hund's rule. That's telling me to put 1 in each of them, and now that's done for the configuration for vanadium. The noble gas electron configuration, we'll do that really quick. I had to put it over here, and I didn't finish writing configuration. I'll just leave it. So for vanadium, if we go back to the last noble gas, so vanadium's here, 23. So if we go back to the last noble gas, that's argon. So we'll put this, okay. So argon is 18. So we can go up 18 of these. So if we go up 2, 4, 10, 12, 18. So we go up 18. That whole area is from argon. So all we need to add on after that, and you see like that shortens it, right? Because all we really need, and we'll talk about this next video, is the electrons that are going to be on the outside, because those are the ones that are going to be involved in bonding and reactivity. So I want you to go back before we start the next video. Maybe watch this a couple times and try to do some of the Alex homework, and then we'll go back and go through these descriptions again, and then I actually have another slide that I can show you that even simplifies it more and helps you follow the pattern even more.